Welcome back, everybody. We're going to go ahead and keep going with our counting. Last time I talked to you about the factorial and what that meant. And today we're going to see a little bit more how that actually is involved in making counts. So let's keep going, folks. So the topic today is called permutations. And a permutation is just a rearrangement. It's an ordering of a set of elements. So you have a set of, I don't know, how about a set of letters? You can rearrange those letters, that's a permutation. You could rearrange them again, that's another permutation. And so that notion of rearranging and reordering is really what's behind the idea of a permutation. Now we know from last time that if we want to permute all the elements, the number of ways we could arrange all the elements was in factorial, right? Think about the number of ways runners could finish. 5 runners could finish in a 5-runner race. How about 12 horses in a race, right? We know that how many different orderings are possible. Well, according to that theorem, 12 factorial. And so I'm not going to show you all the work behind computing 12 factorial. Hopefully you found the exclamation point on your calculator. If not, you can always do 12 times 11 times and so on. But mine is frozen here, so let's take a look here. What's going on? All right, let me figure this out. So we're going to do 12 factorial. Let's see what we get. All right, so I am getting, let's see, 479, 001, 600. So there are over 479 million different orderings of 12 horses. That's how many hypothetical races there are, right? If you define the races, how the horses finish. Imagine guessing the correct finish, guessing all 12 horses correctly. Odds are not in your favor. Well, a lot of times we don't really care who finishes 5th or 6th. Shoot, we don't even care who finishes 4th, 1st, 2nd, 3rd, right? Let's get to the podium. So if we're looking at 1st, 2nd, 3rd, that's a different question, right? How many different 1st, 2nd, 3rd finishes are possible in a 12-horse race? And you know, that's going to be a little more work than I necessarily want to start out doing without thinking about a more efficient way of writing it. So instead, let's start with a simpler problem. Let's look at how many 1st and 2nd finishes there are in a 4-horse race. And if we can extrapolate some things that are going behind the scenes in our count, maybe that'll help us figure out this bigger problem of how many 1st, 2nd, 3rd finishes in a 12-horse race, okay? So just for the sake of simplicity, I'm gonna name my horses A, B, C, and D, okay? And I wanna know how many ways could they finish 1st and 2nd? Well, in other words, I only care about spots 1 and 2. Whoever gets 3rd and 4th, who cares? So we could go A and B, right, for 1st and 2nd, and then I don't care, right? It could go CD or DC, that doesn't matter to me. We could go BA. We could go AC or CA. We could go AD or DA. We could go BC or CB. BD, or DB. We could go CD, or DC. And did we miss any? No, I don't think we did. And so there are 12 possible first, second finishes, right? Well, what we've really asked is how many ways can I arrange R objects out of a set of N objects? So in other words, I have a larger set, N elements, and I want to see how many ways can I just arrange 2 of those? Well, if you think about the horses, there were 4 horses, right? And I want to choose 2 of them. Well, 4 times 3 times 2 times 1 over 2 factorial, which is 2 times 1. We get 12. Just like we counted, okay? So that's an interesting use of permutations, right? This tells me the number of permutations of 2 objects out of 4 is 12. Let's apply this. Password. It needs to contain 7 different letters. How many different passwords are possible? Now, because they're different letters, we're not allowed to repeat the letters, right? So I'm really saying, how many arrangements of 7 letters can I make from 26 letters? Believe it or not, that was a question mark. Okay. So really what I've said is my N is 26 and my R is 7. And so we have 26 factorial over 26 minus 7 factorial, which is 26 factorial over 19 factorial. And we know that once we get to 20, sorry guys, I'm going to move this over a bit. Once we get to 20, then we can cancel out that 19 factorial, right? Because once we get to 19, the rest is 19 factorial. So we have 26 times 25 times 24 times 23 times 21 times 20, which is a very large number. Let's see, 1,000. Okay, so there we have it. Over 3.3 billion different passwords. Okay, so let's go back to this. How many different first, second, third finishes are possible in a 12-horse race? Well, Rn is 12 and our R is 3. How many different arrangements of 3 objects can I make out of a group of 12 objects? And we're told by that lovely theorem that that's the answer. So 12 minus 3 is 9 factorial. And again, what's going to happen once we get to 9? We've got 9 factorial. Those cancel. And we get 12 times 11 times 10. 1,320. Okay. So that's a permutation. And there's two big pictures that I want you to get out of this. The first is that the number of ways you can permute all the objects is just n factorial. And then the number of permutations of just some of those objects is n factorial over that n minus r factorial, okay? And so maybe it would be nice to kind of summarize that. So let's do that. So to summarize, the number of permutations of n objects, this is when you're permuting all of them, is n factorial. The number of permutations of R objects taken from a larger set of n objects is n factorial over n minus r factorial. Okay, so those are the two situations you want to look at. Am I permuting all of them, or am I just rearranging some of them? Okay, that's going to dictate which of these you use. Okay. There's another form of rearrangement that we're going to be concerned with, known as combinations. And when we talk about combinations, we're going to relax the condition that we care about the order. We're going to say, all right, I really don't care about the order. If I don't care about the order that things are arranged, but rather just who is in the arrangement, how many combinations are there? So that's coming next. Before we get there, though, please spend some time looking over these permutations and factorials. Whenever there's new notation, there's just a level of comfort that you need to achieve before you feel comfortable doing the computations. So like I said, get comfortable just with that darn factorial, being able to use it, knowing what it means, and then see it at play when we're actually finding permutations and things. If you want, I can remind you as well that the fundamental counting principle is actually hiding in here, right? If you look back at this 12-horse race, for example, when it was all said and done, your computation was simply 12 times 11 times 10. Well, if you think about that from an event perspective, there were 12 options for finishing first, 11 for finishing second, and 10 for finishing third. So notice that this formula just gives us what we would have seen already with the fundamental counting principle, okay? Similarly, how about this? Whoops. How many arrangements of 7 letters? Well, when it was all said and done, this is what we multiplied by, right? Or multiplied. You've got 7 events. Each event is the picking of a letter. 26 ways, 25, 24, 23, 22, 21, and 20, okay? So the fundamental counting principle is still at play, because after all, we're just counting. This is just a short way for counting, okay? All right. So again, please get used to this. Be familiar with the formulas, the theorems, and all the requisite manipulations. And we will keep going shortly. Okay, take care, guys.